Section 9.5 talks about collisions in 2D. And in a lab frame, it may be worth looking at this. We've discussed in class how if you use the center of mass reference frame, you can treat everything as 1D. But in the lab frame, you can treat it as 2D. May be more convenient sometimes. So in the case of 2D, we know that momentum is a vector. So when we talk about conservation of momentum, that means that momentum is conserved in the X and the Y directions for our 2D case. So if we look at a two-body system, then we have M1V1X plus M2V2X equal to M1V1 final X plus M2V2 final X, as well as M1V1Y plus M2V2Y equal to M1 V1 final Y plus M2 V2 final Y, right? The momentum in the X direction and in the Y direction are conserved. I'm going to state that as component-wise. All right, it's conserved in the X component and conserved in the Y component. So for a classical example here, let's consider two objects like billiard balls. Not necessarily the same mass, because the cue ball has a higher mass. We're going to consider the target as being at rest. All right, so there's a natural way to define our coordinate system. Since only one object's in motion, I'm going to define the X direction in the direction of motion of the one object that's moving. After the collision, so they hit, you have some interaction, and then the balls move away. Something like this. So for mass 1, there's some angle theta 1 relative to the x-axis. And for mass 2, there's some angle theta 2 relative to the x-axis that they exit at. All right, what does this mean for their velocities? So this is our V1 final and our V2 final. Well, if we look at conservation of momentum in the x direction, we have M1V1 plus M2V2, which was initially 0, equal to what? Well, we need components, right? We're going to get our x components of our final velocities. So we have M1, V1 final in the x direction is going to be V1 final times cosine theta 1. And V2 final in the x direction is V2 final cosine theta 2. All right, so cleaning that up a little bit, we have M1 V1 initial equal to M1 V1 final cosine theta 1 plus M2 V2 final cosine theta 2. All right, what do we have in the y direction? So in the y direction, well, we have M1 V1 Y. This should have been a V1 X, really. V1 is just V1 X. So we'll write that on the side. Note, V1 is equal to V1 X, and V1 Y is 0. All right. In the y direction, both initial velocities are 0. So we have 0 equal to m1 v1 final sine theta 1 and m2 v2 final sine theta 2, right? Just taking the components of our velocities in the y direction. But let's be careful here. I'm going to go ahead and insert the direction here because we know that my pen's not working. There we go. The V2 final in the y direction is pointed down, right? So I'm going to go ahead and insert my negative sign there to include the direction. At this point, I'm still talking about them as vectors. And now I've inserted the direction in their magnitudes. So what we end up with here is m1 v1 final sine theta 1 equal to m2 v2 final sine theta 2. Just meaning that since there was 0 momentum in the y direction initially, there still has to be 0 momentum in the y direction, which means the upward momentum of the first object has to be equal to the downward momentum of the second object, right? And that gives us this part. And in the x direction, we have the initial momentum, which was all in object 1, is equal to the x component of the momentum for both objects. Pretty straightforward, expanding it to 2 dimensions. We'll work an example on this in class.